So we have chapters 1 through 5, correct?
Yes.
Okay. We can't cover chapters 1 through 5 in an hour, right? So what were your top topics that you guys wanted to review? Yes.
So I had a question for like polar bonds, polar molecules, and like apolar molecules.
Sure. Yeah.
I actually asked one of my roommates, and she remembered like 2 questions from something she did. So I wrote them down.
Oh, okay.
So now they'd be good like practice problems.
Absolutely.
But at the top is the electronegativities, and then the questions.
Sure. So it might be helpful before we go over these to kind of talk about some general things. It is helpful that the electronegativities are given, so we will look at it from that way. But there's also kind of a shorthand that you might find helpful, save you a bit of time so you don't have to necessarily worry about the math. So let's go over that, then we'll do these practice problems and see how you guys do. Does that sound like a plan? Okay. So you were talking about polar and nonpolar bonds. So that's specifically talking about polar and nonpolar covalent. What type of elements are in covalent bonds? You just started. Sorry, what type of elements are in covalent bonds? So that's an example. So covalent is when you have nonmetal and a nonmetal. This differs from, say, ionic, which you may remember is a metal and a nonmetal. So like an ionic bond. A good example of that would be sodium chloride. Sodium is a metal, chloride is a nonmetal, so them together makes an ionic bond. So covalent, nonmetal, nonmetal. So that could be halogens, but that's anything that's not considered a metal on the periodic table. So let's talk about nonpolar first. So you guys should know that nonpolar, a nonpolar bond happens when you have a difference of electronegativity that's less than, is it 0.4 or 0.3? 0.4, okay, that's what I thought. So a difference less than 0.4. That's helpful if you're given the electronegativities, but you may, for example, I think there was, oh no, he did give you the electronegativities, but you can actually figure this out without having those numbers if you're ever in a situation like that. So the way I like to think of it is actually a game of tug of war. So you have a flag in the middle, okay? Now, if you were to have something that's diatomic, okay? So like H2. It's just H and H bonded to each other. If you had 2 twins, identical twins that were truly identical in every way on either side of a tug of war, is this flag going to move at all? No. So if this flag is the electron's going to pretty much stay directly in the middle, okay? So for when we're talking about polar versus nonpolar, polar would have charges, would have a dipole. So if the electron doesn't move, there's no charges, okay? So anything that's diatomic, I used H2, but you could also have 2 halogens together, or oxygen. Anything that's diatomic, you would have no difference in electronegativity, so nonpolar. Can anybody else think of an example that's not diatomic, where you'd still have a nonpolar bond? Not diatomic, but still nonpolar. Yes?
So, can't give you the exact elements, but
Okay.
if you had 1 element on one side and 2 on the right, but their charges canceled?
Okay, so that's looking at a molecule, right? Because you couldn't have, basically that would be 2 separate bonds, right? So if we had something bonded to 2 different things, we'd have another tug of war over here in a sense. So if you did have something that was completely symmetrical, that would be the case. I'm actually thinking of something that makes alkanes all nonpolar. So anytime you have carbon bonded with hydrogen, that is also an instance of a nonpolar bond. And that difference in electronegativity, if you were to figure it out, is right at 0.4. Okay? So even though it's not diatomic, this is kind of a poster child of nonpolar. So if you're talking about alkanes, that only have carbons and hydrogens, that's all nonpolar bonds, right? So alkanes are nonpolar molecules. Is everybody still with me? Do you need to repeat anything? Okay. Can I move on to polar? Okay, all right. So polar bonds, higher than 0.4. You actually get into a realm where you do get to ionic, but you don't have to worry about that for this class. So the shortcut way of determining this, so you want something with a big difference in electronegativity. So the key is to know who your weak electronegative are and your really the strongest electronegative are. So in terms of your weak ones, these are really your two weakest ones. Okay? Can somebody name some of the stronger electronegative atoms?
Fluorine.
Fluorine's the strongest. Excellent.
Chlorine. Bromine. Iodine.
So we named the halogens. That's good. There's two more that I'm thinking of that are
Oxygen.
oxygen and what's next?
Nitrogen.
Very good. So on the periodic table, these 6 actually make kind of like a 7. So that little corner, those are your most electronegative atoms. So anytime you have one of these with one of these, you have a polar bond. So some examples. Okay, so oxygen with hydrogens, polar and polar. The electron's going to move closer to those oxygens, making the hydrogens more positive. Here, the carbon-hydrogen bonds we know are nonpolar, but because this carbon is bonded to a chlorine, the chlorine is going to be more negative, the carbon more positive. Okay? Are we okay, all set for these example questions? Okay. Okay, so this first one. Which of the following have polar bonds? Okay? Anybody want to throw out a guess for which one of these has a polar bond? Yes?
A and D.
A and D. So let's take a look at that. Okay? So if we were to draw these out, you can imagine the hydrogens. So oxygen is bonded to both a hydrogen and a carbon. So here the oxygen would be more positive. Oxygen would be more negative, and the carbon and hydrogen would be more positive. Very good. And the same thing is happening here. We just have another carbon on the end. Does everybody understand why A and D are the correct answers? Awesome. And I'm actually going to add my own to this one, because we didn't quite talk about it, but it's a good choice to review. So this one, which are the polar molecules, and then by default, which are the apolar molecules?
Are A and D the polar ones?
Okay.
And possibly E.
Possibly E. Does anybody have any comments on that? Do you guys agree?
I think E is polar.
Okay, so I get some for polar. Does anybody think E is not polar for any reason? This is a trick one. These are obvious, yes. Good.
I
So
assume it's not because you put it there, but I would have thought it was polar if you didn't.
yeah, so
like,
let's talk about this. And this actually, I don't know your name. I saw it. Kate. Okay, that's fine. So Kate brought up a situation where polar bonds cancel each other out, making something nonpolar, if you guys remember that. So if a molecule only has one polar bond, the molecule itself is going to be polar. When you get into situations like E, so if we were to look at this molecule, it would be a perfect tetrahedral shape, and we have identical bonds all the way around. So this would cancel out this, and this would cancel out this. So the molecule itself is actually nonpolar. He may throw something on like this on. This is a pretty good example of a nonpolar molecule that has polar bonds. But in the grand scheme of things, he's going to give you partial credit. So even if you were to circle this, I would recommend following your gut rather than missing something, because this again is kind of the exception to the rule. These are, you know, kind of the standard, what you would expect. So that's a tricky one. I hope that he doesn't put that on there, but I'm glad that you brought up that specifically so we could review it.
So what is the definition of polar molecule? Like, it's
Sure.
just...
So polar molecule, okay, so you can think of it as a molecule that has dipoles, okay? So the only caveat or exception to that is when the dipoles cancel each other out, okay? This still has dipoles there, but because they're equal and opposite, overall they cancel out. But in the general scheme of things, something that has a dipole or a polar
Well,
bond,
if it has a polar bond, it's a polar bond.
unless they cancel each
Unless
other.
they
Yep,
cancel.
yep.
Okay.
I'm being recorded. I have to be careful what I say. Any questions on this? Okay, this was great. Thank you for bringing that in. Any other topics of interest?
So like anything that has like R and S in like chapter 5.
R and
I'm
S,
so
okay.
confused about that.
Sounds good. So, absolute configuration. So before we get started on this, I want to remind you that absolute configuration is not optical activity. Okay, we'll talk a little bit more about that, but I don't want that to be a confusion from the start. Okay, so absolute configuration is mutually exclusive from optical activity. So optical activity is that dextrorotary or lever rotary. Even if you know that, that doesn't necessarily dictate the absolute configuration, so don't get confused on that. Okay, chapter 5. Okay, so let's start with an example. So here we have a chiral carbon, right? A chiral carbon is just an asymmetric carbon, so it has 4 different attachments. To figure out absolute configuration, you're focusing on the atomic weight of these substituents, okay? And it's also the atomic weight of what's directly attached. So here we see a substituent that has multiple attachments. We're going to be focusing on just the carbon, okay? So out of the carbon, iodine, chlorine, and hydrogen, which one of those has the highest atomic weight? Iodine, exactly. The other way of thinking of this, if you can picture the periodic table, the lower down, the higher the weight is going to be. I'm sure you guys know that, but just another way to think of it. Okay. What would the second highest atomic weight be? Chlorine. Third? Carbon. That leaves the hydrogen. Okay. So, absolute configuration. You start at 1, go to 2, and just keep going all the way around. So, start at 1, go to 2, keep going that direction. So this is going clockwise. So that's R. Okay? Let's look at kind of the same but slightly different.
Wait, does it matter even if like the 4 is in a weird place? It's just like the 1, 2, which
Yep, and just keep going around. Yep. Good question.
Atomic weight.
Yes. Okay. So with this one we have the same attachments, so we're going to have the same numbers. Iodine 1, 2, 4. So start at 1, go to 2, keep going around. Counterclockwise, S configuration. Do we want another example?
So is that like all it means?
That's all it means.
And
What's the point of it?
So notice how, so this is important for distinguishing between enantiomers, right? Okay, so if we look at these two, same molecular formula, slightly different connectivity, right?
Oh, right.
Okay, so enantiomers are going to be R and S.
Got it.
Are you going to ever use this? I can't promise that. Does that kind of help a little bit?
Yeah.
And before we leave off, I'm just going to reiterate again. If you know the absolute configuration, that does not mean you know the optical activity. Mutually exclusive. One does not determine the other.
And this is the absolute configuration.
Yes. Optical activity is your dextrorotary and levorotary.
Can we go over that?
Sure. Can I erase this? Okay.
There was a question on the quiz
Okay.
that, like, can you see it or can I say it out loud?
Let me take a look at it.
He kind of explained it.
Oh, sure. Oh, okay. Yeah, so I'm just going to read it up here so people. So this is from chapter 5 quiz. A chemist believes she has isolated a pure R of an enantiomer. She assays a sample in her polarimeter and should see, these are the options, dextrorotary, levorotary. She cannot know which rotation she will see. Circle your answer. So again, R refers to the absolute configuration, so she can't hypothesize what the optical activity is going to be. Okay, but let's talk a little bit. I'll bring this back to you in a second. So optical activity has to do with the fact that enantiomers rotate polarized light. Okay, and that's because they're chiral. Okay, so you can't have optical activity without something being chiral. Okay. Now, you can visualize this through a polarimeter, okay? Or you guys have used refractometers, so it's a pretty similar process. Because you can have enantiomers can rotate it one way or the other. If it's rotating it clockwise, that's dextrorotary. So that says clockwise.
Which is R, right?
No.
R and S are only for absolute configuration.
Yep.
So
Optical
dextrorotary
activity is
clockwise.
Keep the wall in your mind. Don't let them cross over the wall.
Oh.
I know it's difficult because they come right after each other in the notes.
There's the absolute configuration, absolute.
There you go.
Okay.
Perfect. So then counterclockwise would be levorotary. I'm pretty sure I spelled that wrong. So again, it's just referring to the direction that light is being rotated. Does anybody remember what the solution is called when you have 50% rotating clockwise and 50% rotating counterclockwise? Racemic. Okay? Yes.
So, can you just go over what optical activity is overall?
Yes. So it's the rotating of polarized light. That's the definition overall. There's.
Polarized light.
Yep. In reality, you're probably going to be asked questions, where he gives you something's going clockwise or counterclockwise, and you need to know what that means in terms of dextro or levero. Okay? Don't make it more complicated, okay? Sorry, I lost the place. Racemic. Okay, yes. So when you have 50% rotating clockwise, 50% rotating counterclockwise, that's racemic.
And you don't see any rotation.
Right. So this is optically inactive. Okay. Okay. If I'm talking about a meso compound, Would a meso compound have optical activity? Why? I heard no's.
Isn't it like a mirror image of itself and is superimposable?
So it is, right, so it's not chiral. So if something is achiral, it is optically inactive. You have to be chiral to have optical activity. So achiral is not optically active.
And chiral is just, in the notes it says like it has the same, I should have shown it.
Yes.
It's like a mirror image, it can superimpose on itself.
So chiral is asymmetrical.
Oh, I lied, never mind. It says achiral. It has the
Yep,
same.
yep. This is kind of probably the most frustrating thing about organic chemistry.
Racemic is optical intact, which means you don't see movement, right?
Right, no optical activity. Yep, yep. So if something is chiral, it has at least one asymmetric carbon. If something's achiral, it has some form of symmetry in the molecule. Okay? Okay. Will there ever be a case where an enantiomer is optically inactive? One enantiomer. Why? I heard no.
Is there identical?
So if we're talking about one enantiomer, so are enantiomers inherently chiral or achiral?
Oh.
Right, exactly. So enantiomers are always chiral. You have to be chiral to be an enantiomer. So every enantiomer is always going to be optically active, unless it's mixed in a racemic mixture. That's the one caveat there. How do we feel about optical activity and absolute configuration?
Better. Is this one for diastereomers?
Sure. Versus enantiomers or just in general?
Just in general.
Okay.
Could we do the versus as well?
Sure. It kind of lends itself to a compare-contrast. I think I need to try this out. Okay, so let's first talk about the definition of these two, because that right there will tell you a lot of information. So both of these are referred to as stereoisomers. Okay? This differs from what you talked about, I think, in the first or second chapter, which are called constitutional isomers. So make sure to try and keep those separated. Stereoisomers have the same molecular formula, but differ in connectivity. So basically, they're rearranged differently in space. That's a different way of remembering it. Actually, I'm sorry, I wrote that wrong. Same connectivity, differ in arrangement.
Same molecular formula and connectivity, but different arrangement.
Yeah, I apologize.
I said different in space because then I remember stereo in space.
That's a good way of thinking of it, absolutely. Okay, so this applies to both enantiomers and diastereomers. So the only difference is enantiomers are related by a mirror plane. Which is just a fancy way of saying they're mirror images of each other. And diastereomers are not related by a mirror plane. So they aren't mirror images of each other.
So when it says mirror, it means like if you sandwich them together, they'd match up, right?
Yep, exactly. So anytime you see a dotted line like that, that's referring to a mirror plane. So if you were to sandwich them, just like you said, you would see that the CLs would match up the BRs, the Fs, and the Hs. The important thing here, though, if you were to superimpose them, they would not line up. This CL would line up in front of this H would line up in front of that CL. So that's what makes them different molecules, okay? Because you can't have enantiomers that are the same molecule, okay? So related by a mirror plane, rearranged differently in space, but they're still technically different molecules.
So they're not superimposable.
Yes, not
Is that what
superimposable.
makes them enantiomers?
Enantiomers, yes, makes them chiral, perfect.
Which ones can be separated?
So they both can be separated. It's a lot harder to separate these ones, though.
Okay.
And the reason for that, because as you can see here, they're nearly identical. It's really almost impossible to tell the difference between them. And they have all the same physical properties. So they have the same densities, the same melting and boiling points, etc. So it's really difficult to separate them. The only way is through a process called resolution, which you talked about chiral chromatography in class. Okay, so this would be an example of diastereomers. So we would have the same molecular formula. The carbons are attached to the same numbers of bromines and hydrogens. That hasn't changed. But we can see here that they're not mirror images of each other. Here we alternate BRs. Here the BRs are all on the same side. So this is just one example. Does that help?
And they're achiral?
So diastereomers can be chiral or achiral. Unlike enantiomers, which are always chiral, it just depends.
They can't be
Wait.
superimposable.
These are-
Enantiomers are always chiral?
Always chiral. Diastereomers can be chiral or achiral.
Can you put one more example of the diastereomers?
Sure. Just gonna erase this side just. So this was one with an alkene, so it's a little bit different, but we can see this would be cis and trans, right? So cis and trans is actually a perfect example of diastereomers. So anytime you see that sort of relationship, you can automatically go to diastereomers. Yes,
So for them to be diastereomers, they have to, whatever,
don't worry about it.
they have to like have the same components and make up, like they can't be like too random, right?
Exactly.
That's what makes it a stereomer.
So the big umbrella thing with isomer, right? They all have to have the same molecular formula.
Okay.
Okay, that's number one, with constitutional or stereoisomers.
Okay.
Yeah. Yes.
I have a question, but it's not related to this. What do we need to know about homolytic and heterolytic cleavages? or something?
Sure. Yeah. So in homolytic cleavage, what's your final product?
They're the same.
Two of the same what?
Free radicals.
Free radicals. Okay, know that. And heterolytic cleavage, what's the final? What do you get with heterolytic
Cations
cleavage?
and anions.
Good. Ions in general. Very good. So, you know, if we're just talking about those two brief definitions, definitely knowing the products are important. He may kind of build that into another question, possibly talking about the radical chain reaction. So you could need to know homolytic cleavage is involved, but in terms of what you need to know specifically about homolytic, know what's happening, right? That's the important thing. Any questions on enantiomers, diastereomers, this kind of stuff?
For diastereomers, can they be superimposable ever, or?
So they are not mirror images, right? So to be superimposable, you would have to be mirror images of
Oh,
each
okay.
other.
Thank you.
No problem.
Can you not erase the second example?
I will not erase the second example.
I'm so sorry.
No, you're fine. Yes.
Can we go over ring stream?
Sure. You guys came prepared. It makes my life easier. I'm gonna erase the round, the second example, okay?
You can actually erase it now.
Oh, okay.
I can't remember.
Also, do you know if he gives us like the formulas for like stereo centers and stuff like that?
I wouldn't expect him to. He may or may not, but I wouldn't
You guys
expect him
have
to.
no idea what I'm talking about, these two. So, like,
Oh, yeah, I know what you're talking
yeah.
about.
And,
Homologous series and.
yeah. So you just have to remember those.
Wait, what's the question?
Well,
Yeah,
I did a
what?
picture of that. Yeah. So this is stereo centers,
Oh,
which is to the N power, and then this is like when he gives you 69 carbons, you would put the.
Oh, he gave it to us the last quiz. He did give it to us the last quiz.
Yes, but midterms and finals are different than your quizzes. So any hints that he gives you, I wouldn't expect that to be there. He may give it to you again, but I just wouldn't expect it.
Okay.
So a question about ring strain. So let's start with the 3 types of ring strain.
What packet are you
This is chapter 4.
Is it eclipse, transannular, and bond angle?
Good.
Be honest, in the evening.
I love Latin.
Okay. So the 3: substituent eclipsing, transannular, bond angle, which you may also know as ring size. I spelled that right. You talk a lot in this chapter about ring size because that's kind of the most visible, and it does explain a lot. So out of your cycloalkanes, which one has the most strain? Cyclopropane, excellent. So most strain. You don't need to know the specifics in terms of, is there more transannular or more eclipsing or things of that nature. I wouldn't focus on that. It's more about just the general concept. What cycloalkane has the least amount of strain? You guys will get those questions right. So again, it's more important that you know the 3 types and you know some general characteristics about how ring size affects these. When we talk about cyclohexane, it can have 4 different conformations. What are the 4 different conformations? 4 different conformations of cyclohexane.
So is it like twist boat, chair, half chair, half boat?
No, there's only 4.
Yeah, can we go over those?
That's you put it in the group.
So boat, twist boat, chair, half chair. Okay, which one of these is the most stable? Chair.
Did you say the half chair?
Just thinking.
So close, so close. Okay, which one is the least stable?
Half chair.
Half chair. Okay. Just so you know, in terms of order, okay, there's kind of an easy way. If you remember that chair is first and half chair comes second, it's 1 word, 2 word, 1 word, 2 word. So chair, twist boat, boat, half chair.
What are the numbers for?
So this is in terms of stability. So most stable, least stable.
Oh, okay. And it goes, okay.
So 1 word, 2 word, 1 word, 2 word. Chair, twist boat, boat, half chair. Again, don't spend time focusing on the fact that this one has more substituent eclipsing strain than boat, and that's why it's considered less stable. He's not going to ask you questions on that. I'm honestly, these may be the 4 questions that he asks you for chapter 4 on the midterm. Okay, he might give you one of for example, we talked about bond angle strain in class. Name the 2 other types of strain that can affect, a ring. What is what cycloalkane has the most strain, or what cycloalkane is the most reactive, most unstable? All of those would be cyclopropane. Putting these in order or answering, least strain, most strain. There's only so many ways that he.
Do you think he's gonna ask us to draw, or like circle which one's twist boat? Because I don't really know the difference between like chair and half chair.
No, those are pretty difficult to decipher pictures, and he is not going to draw those and expect you to differentiate. So don't take it that far. You may have to draw skeletal structures. That's absolutely up for grabs, with and without substituents. So these are now up for grabs in terms of naming and drawing. Any question? Oh, sorry.
Cyclopropane is most strain, right? And most stable?
No. Most strain, least stable. Very, very unstable.
More strain, more unstable.
Yes. A way of thinking of it, so if there's a lot of strain, that means that all of the atoms are kind of fighting against the formation that they're in. So that takes a lot of energy to keep in that formation, okay? And that's not a good thing, right? We don't want to have to use extra energy to keep something from, exploding in a sense.
I have a class.
Okay.
This is very helpful.
Okay, good. Good luck tomorrow. Any more questions on this? You had asked about the strain question. Did I answer your question? Was this what you needed?
Yeah.
Okay, great.
Is this only for cyclohexanes?
No, this is for any.
This is for everything.
Sorry, I meant.
No, that's okay. This is regarding cyclohexane. But this strain applies to any cycloalkane.
So you don't think he would ask anything more other than all of this?
Okay, so I'm being recorded, so I definitely can't promise that he won't, but I think in terms, the way I like to look at these chapters, what's the meat and potatoes? This is the meat and potatoes of this chapter. Yes, there are a couple other things like Gauss interactions that are up for grabs.
We can only ask so many. There's only like 60.
Gauss interactions are a possibility though. So that has to do with when you have bulky substituents on the ring. So you can have things in either axial position or equatorial position. What does axial mean?
Axial means above and below.
Okay, good. And equatorial?
Lateral, zigzags, left and right.
Another way of thinking of it is in the same plane. So above, below the ring, in the same plane as the ring. Excellent, very good. So do you guys all have Dr. Cosper's notes handy?
Yeah.
Because I can just reference a page in chapter 4 instead of drawing it. So page 3, chapter 4, and we're in about halfway down 4-4. So basically you have a cyclohexane with a methyl group attached. Okay, now this can either be in equatorial position, so in line with the ring, or it can be in axial position. It's shown at below the ring here, but it could technically be above too. So if you look at the one that is an axial position, you'll see these little dash marks, okay, next to the methyl group and the two hydrogens next to it. Basically, that's referring to Gauss interactions. I'll write it up here. Oh, goodness. Okay, so this is just when you have a big bulky group that's interacting with the hydrogens nearby. Okay, it causes a little bit more strain. So that's why substituents are more favorable in the equatorial position. So substituents more favorable in the equatorial than the axial. But that would be an example of something else that is technically up for grabs and is a little popular. And then other things like terpenes, isoprene, and steroids. But I think all of those were on your quiz. Yeah.
Terpenes, I thought, yeah.
Sure. Can I erase this?
Yeah.
Okay. So terpenes is just a big umbrella term for a variety of compounds, okay? And the one thing they all have in common is this unit called the isoprene unit. So any molecule that has this unit somewhere within it, and it could look very different, you could have different substituents, you could have some double bonds in there, it would be considered a terpene. That's all it is. So a terpene is something that has an isoprene unit within it, somewhere in the molecule.
Is that a skeletal structure?
This is, yes. So
Not like half of a cyclohexane.
so it would technically look like that a little bit, yes. But just imagine carbons here, yeah. So, like for example, this is the one that's in her notes. This would be an example of a terpene. Okay, so you can see the isoprene unit in there, but there's been some modifications to it. In the past, I don't know if this is something he'll do, but he has asked for, an example of a terpene. Okay, so like Taxol, camphor. I think he named a few others.
Are these like, because he asked us, he wanted us to name a natural product of a
Yep.
terpene.
A natural product of a terpene?
Yeah, he said terpenes are natural building blocks and we're trying to implement natural products and make them.
Oh, okay, then
Totally
yes.
yes.
Yeah, so, which one is it? Sorry.
I said essential oils instead.
His examples he did was like rose, amber, and
Okay, yeah,
Oh,
so,
okay.
and then in Dr. Cosper's note, she does list some examples, like specific examples, but. We good with chapter 4? What's next?
What do we need to know about resonance?
What chapter did you talk about resonance?
Yeah. It's like third. Five?
I don't know.
I'm surprised that he would bring it up this early. Chapter 3?
Yeah, that's easy, because that's when we went over orbital hybridization.
Oh, okay.
Right?
Yes. So I have a feeling you won't necessarily see too much on resonance for the midterm. Again, I can't promise anything. Resonance is going to come up a lot more in your later chapters, so I would expect more questions there. I'm going to talk about resonance in a very general sense because I don't think that you're really going to see too many questions, but just in general. Does anybody know what this molecule is? Benzene. Who said it? Okay, awesome. Good. Okay. So, why do I have a circle drawn in the middle of the, what does the circle refer to?
Alternating double bonds.
Excellent. Somebody was paying attention in general chemistry. So alternating single and double bonds. So why do they draw it with a circle? Why don't they just draw it like this?
I don't know.
Okay, okay. So this could also be this. Now essentially, when you have single and double bonds right next to each other, the electrons in the double bonds will move towards the single bonds and back and forth. So you may hear the term electron delocalization, which is just a fancy name for electron movement. Okay, that's all it means. Delocalization out of its normal position. So these electrons can shift here, and then go here, and then go here, and then go here. Oh my gosh, it's a circle. So resonance is just electron delocalization. It's just electron movement. It happens a lot in alternating double and single bonds, so you're going to see it when you talk about alkenes, carboxylic acids, things of that nature. Yes?
Can you go over initiation and propagation?
Sure. So with these, I highly recommend knowing what's happening in those steps, okay? Because when you think of what questions can he ask, a really simple one is what's the product of propagation 1, right? So that's a pretty simple question he could ask you.
Because the electrons can move between single and double bonds. So it's exactly the same thing. Just shows it.
So initiation, in Dr. Cosper's notes, and I think in class he used chlorine because that's most typically used in industry. So I'm going to continue with that. So the first step of initiation is homolytic cleavage. And what did we say happens, what's the product of homolytic cleavage? Two radicals, excellent. And remember that a radical is just something with a free electron. So I'm going to draw some shapes because it's easier to see where these radicals are going.
What is the whole initiation propagation system called? Like
Radical chain reaction.
Radical chain.
And don't forget the last step is technically termination. Okay. Okay, so one of these chlorines is going to move on to propagation 1. The other one is going to float around in the system. It's still around, but it's not being used right now. This chlorine is going to react with this carbon group. In this case, it's methane, but it could be any alkane. Okay, alkane. We're going to have another round of homolytic cleavage here. Okay, so we're going to end up with an H radical, and a carbon radical. So homolytic cleavage of the alkane gives you 2 radicals again. Okay? This chlorine and this hydrogen are going to come together. And then we're going to be left with our carbon radical. Yes.
Okay. So my question is, could it be any of the hydrogens that come off and connect with the chlorine?
Yes, in this case, because they're all the same hydrogens.
It doesn't
Okay.
matter.
In this case.
Yeah.
So the other thing to think about, which we can talk a little bit more about, so you can have primary, secondary, and tertiary carbons, and some of those are more reactive and more stable than others.
Okay.
So we'll talk about that a little bit, but I kind of want to keep going in a linear direction. That's a great question, though.
Okay.
And so, in this case, we have a methyl radical because it's 1 carbon, but in general, we're making a carbon radical.
Okay.
So, initiation, chlorine breaks up into 2 chlorine radicals. Propagation 1, a chlorine radical reacts with an alkane to create a carbon radical. This is less important. He's probably going to ask a question that's regarding this. How do we feel about propagation 1?
Okay.
Okay. So this is where it sometimes gets a little confusing. So remember that we're in, a system that has a bunch of chlorine gas running around. So this methyl radical is going to react with another separate chlorine molecule. Again, we're going to get some homolytic cleavage. Okay? And one of these chlorines is going to react with that carbon radical that we just made. So we end up with, basically you can think of it as the chlorine taking this spot. Yes. What's your question?
So why can't the carbon radical hook up with the other chlorine radical from initiation?
So technically it could. Okay, this is a very simplified view. And remember, you kind of have this sea of molecules floating around.
So it goes really quickly?
So it could, if it, if it collides with it, it's going to react with it. This is just showing that, in reality, is it really going to find that one chlorine radical from before? Probably not. It's probably going to react with whatever it's close to.
Okay.
Good question, though.
What type of cleavage in propagation 1?
All of this is homolytic cleavage. All of it. Homolytic, and because you can see here we're making radicals again, right? Making radicals. So, our methyl radical or carbon radical reacts with chlorine, making chlorine radicals and a haloalkane. This is the most important piece because this is the entire purpose of the reaction. They set out to make a haloalkane, and so that's the final product of propagation 2.
Where does the HCl go? Floats away and
Yep.
then it's ready to be.
Floats away, and these chlorine radicals can react with each other. They can react with other molecules. Basically, they're just floating around reacting with whatever they collect. It's going to keep going, exactly. So it'll keep going until we run out of them.
So the triangle C chlorine goes with the carbon radical to make the
Yep.
haloalkene.
Mm-hmm.
So 2 carbon atoms. 1 carbon?
No.
One
that's
carbon
combination
radical.
2. Never mind,
Yep,
never mind, never mind.
Okay, so let's take a step back because an important point was brought up. So your alkane here, not all alkanes are created equal. In terms of bond association energy, okay? So the classification of the carbon is going to indicate how much energy it takes to make the radical, okay? So you can have primary, secondary, or tertiary, or methyl, technically. Okay, these are all carbon radicals, okay? In terms of energy to form, so energy to form, stability, let's do this, sorry, reactivity, and stability of radical. Okay, so let me explain this a little bit. So methyl, primary, secondary, tertiary. It takes the most energy to break up this hydrogen from this methyl, okay? It takes much less energy to break it off from a tertiary carbon. In terms of reactivity, the more stable the radical is going to be, the more reactive that carbon is going to be, okay? So basically, it's just the molecule being lazy, okay? If it's going to take a lot of energy and make something unstable, it's not going to do it. So the more stable the radical is going to be, the more reactive the alkane is. Any questions on this? What is the force that stabilizes the carbon radical? Starts with an H. Hyperconjugation. Super important. Okay? Force that stabilizes the carbon radical.
Can we go over prop 2 again?
Sure, yes. No problem. Prop 2. So we have a carbon radical made from prop 1. That's going to react with a chlorine molecule, which makes 2 radicals, one of which is going to react with the carbon radical to make a haloalkane.
So hyperconjugation is important. Why?
So it has to do with the stability here, okay? So I said that as we increase classification, we become more stable. That's because of hyperconjugation. If we didn't have hyperconjugation, we wouldn't have any stability in these carbon radicals. If you reference, what chapter are we even in? Chapter 3. Page 2, when it's talking about the radical chain reaction, there's a really nice diagram which shows the different types of radicals. So from methyl, primary, secondary, and tertiary. So if we look at primary, secondary, and tertiary specifically, you can see these dotted lines near the, basically connecting the tops of the carbon radical and the sp hybridized of its substituents. That's hyperconjugation, okay? So without that, you would have no stability and you wouldn't be forming your products.
Okay, so hyperconjugation forms stability.
It's the force that gives stability. Any more questions about the radical chain reaction?
Did we go over termination?
Oh, so termination, in the notes, basically you just have a variety of radicals coming together, but one example of this, so we had circle, so if we remember our circle chlorine from initiation and our diamond chlorine from propagation 2, so those chlorines are again floating around, okay? If they collide with each other, they'll react and make another chlorine molecule. They could also bump into another methyl radical because again, this is all happening, all over the system. They could bump into a hydrogen floating around from this breakup here. So essentially you just have a bunch of radicals floating around, bonding, falling apart again, until we run out of chlorine radicals in general. Once we run out of chlorine radicals, the reaction stops. Good question. New topic?
Where to go with PKA?
PK.
Before we end, can you touch on formal charge too?
Oh, okay. What questions has he asked about formal charge?
I don't know what that
It's
in his notes. It's in his notes. It's in the PowerPoint.
Which one?
I was gonna say, what section is that? Oh,
If you're not
resonance?
concerned, I'm not concerned.
I'm just surprised, I guess.
If you're not concerned, I'm not concerned.
Yeah, I'd be really surprised if he threw something on there with formal charge.
They're all blending together.
If there's a formal charge on there, please don't be angry with me, but I'd be very shocked. Okay, PKA. So a lot of people get hung up on what the definition of PKA is, and really it's just essentially it's related to Ka, which is the acidity constant. So essentially you take the negative log of Ka and you get your pKa. More importantly is what it means, okay? And so this can tell you a lot about the how strong of an acid. So the lower the pKa, the stronger the acid. One thing that he really likes to quiz you on, and I'm pretty sure it was on your quiz for this chapter, is the relationship between pKa, pH, and dissociation, okay? So, for example, if you have an acid with a pKa of 1.7, okay? And the solution is at a pH of 1.7. How much of that acid has been disassociated? 50%, the magic number. What does disassociated mean? Comes apart, breaks apart. Good. So 50% is broken apart. Okay. He could also maybe flip the wording a bit and say, the pKa of an acid is 1.7. 50% of the acid has been broken up. What is the pH of that solution? So again, in this scenario, the pH and the pKa are matching, and it's always 50%. He's never going to give you a situation where they don't match, because he's not concerned with you doing the math. Okay? That's not what he wants you to focus on. He could also have you compare. So acid A has a pK of 0.005. Acid B has a pKa of 5, which is the stronger acid. A, because it's whatever one is lower. Any other specific questions? Did I answer the pKa question? Is that okay?
Yeah. Is that all we have to know?
So I don't really think there is really much other content that I know of. There is formulas in Dr. Cosper's notes that you won't have to use. So yeah, I think this pretty much covers it. But again, you can't quote me. Yes.
And
Can we go over the
The what? Sorry.
Gibbs?
Oh yeah, sure. You had a follow-up question?
the 50% broken apart, it's a constant, right? It's like always 50%.
Yes, in this situation. So whenever the pKa and the pH are the same, 50%.
So what? Then we won't have to worry about.
Nope. Okay, Gibbs free energy. So delta G equals delta H minus T delta S. So you won't have to do math with this as far as I know. It's more about understanding what each term means and how it applies to the thermodynamics of the reaction. So Gibbs free energy is delta G. And with this, you're really focusing on sign. Yes.
Is that what you want it to be? Like you want the 8?
So we're gonna talk about these. Okay. So delta G can be negative and or positive. Okay. Which of these is considered favorable? Negative or positive? Negative. So a positive delta G is considered unfavorable. Delta H. What does delta H stand for? What's the name of it?
Enthalpy.
Enthalpy. Good. Okay. Negative or positive? Which is favorable? Negative again. Good. Okay. And what is delta S? Entropy. How do we keep enthalpy and entropy separate?
Entropy is order.
Oh, okay.
Oh, is
That's
that what you mean by that?
yeah. Like how do you keep them straight in your mind? Because you're enthalpy. So my way, you can use whatever way you want. Enthalpy has an H in it. Whichever way works for you. So in this case, negative or positive, which is considered favorable? Positive. So this is the one that's different. This is the one that usually throws people up. So those three values can determine the favorability of the reaction or the extent to which it's going to take place. Did you have any other specific questions, or was this what you were looking for?
When it, like, there's the A and the B and the K and the.
Oh, okay, so that's actually separate. That's good.
Oh,
That's
okay.
good. So I'm glad you brought that up. So this is one way that you can determine the thermodynamics, okay? But equilibrium is another way. They're actually separate, okay? So I think Dr. Cosper just wrote K, but you could also see it as KEQ. So this is the equilibrium constant. And you can find the equilibrium constant by comparing the concentrations of reactants and products, okay? So the concentration of products goes on top of the fraction, concentration of reactants on the bottom. So this gives you the KEQ, and the value of that can tell you, again, whether it's favorable or unfavorable. So whereas this is negative positive, this is just less than 1 or greater than 1. Both signs are going to be positive, so that's why I want to keep them separate. So if K less than 1, okay. So if K is less than 1, do we have more products or more reactants? Reactants. So think of it like a fraction, right? So if you have a bigger number on bottom, right, that's going to be less than 1. So we have more reactants. If K is greater than 1, that means we have a bigger number on top. So we have more products. Okay, so what does that mean? I like to think of it as a business, okay? So if you are running a business, you would rather be selling more product, right? Shipping that product out. It's not really a great thing if you have to bring in unsold product back to the factory, right? That's not an ideal situation. So this is considered favorable, having a K that's greater than 1. This is unfavorable. Ooh, I'm not going to circle that because that's confusing. So having a K greater than 1, you can assume, well, you would know that your delta G is negative because that's favorable and this is favorable. Okay, so those are how they do have a relationship, but they're technically separate concepts. Okay, so you're never going to have a negative K. Okay?
And you want K to be greater than 1.
Yes, greater than 1. So he could, for example, he could give you, I think this is how he did it on your quiz, you know, if you have a K of 0.001, is that favorable, unfavorable? Doesn't matter. This would be unfavorable because it's less than 1. Usually he does extremely low, like small numbers, or like extremely big, like a million, a K of a million. So like he doesn't give you like super close ones usually.
And then if the arrow's pointing towards the A or the arrow's pointing...
Oh yeah, that's how he did it. That's how he did it, right? So we've got. So these are two different scenarios. So the bigger arrow is showing what's being made more of. So here we would have more B, so this would be a favorable scenario. Here we would have more A being made, so this would be an unfavorable scenario. So we're actually a little bit over time. We did start a couple minutes late, but any last minute questions? You guys feel ready for this midterm?
That's a good one.
For those of you that weren't here last week, weren't on the review session, the Zoom. The one thing that one recommendation or suggestion would be to take your quiz questions and look at it from both sides. So for example, if he asks you a question and it's a multiple choice, remember that he could also ask that question in a fill-in-the-blank scenario. So definitely don't rely on the formats being the same. If he asks you, like if he defines something and then asks you to fill in the blank, he could switch it around and say, ask for a brief definition of what he had kind of explained in the quiz. So know both sides. Yep.
I forget what it's called, so this is probably not helpful. It's like a circle, and there's
Staggered and eclipse.
yeah.
Sure.
Sorry.
No, it's okay. That was a very good explanation.
Good luck at physics.
Good luck. Okay, so here we are just looking at ethane, but we're looking at it from a different view. And if I would recommend actually following me upstairs because we have one of those molecular units that you can put things together, and it's helpful to see it in person. But so essentially, this is the molecule that we're looking at. But instead of looking at it like this, so pretend this is the carbon here and this is the carbon here. Instead of looking at it from this way, we're actually looking directly at it. So the carbons are in line with each other, and the carbon's actually like poking out at you. Okay? Does that kind of are you oriented to what this looks like?
Where would that be on the circle?
So carbons are right here. Right in.
Like,
Yep, exactly.
Picture like a paper towel too. If
Perfect.
you hold it like this way,
Very
the
good.
carbons is the cardboard.
So-
and then you turn it towards you and you're looking down. And the
Yeah,
circle is the carbon.
that's a perfect analogy. So because we have a single bond here, the carbon can rotate. So these hydrogens can move in our field of vision. So here we have the hydrogens perfectly spaced apart. This is staggered, right? Makes sense. The hydrogens are staggered away from each other. And you can also rotate it so that the hydrogens are directly in line with each other. So they're eclipsed, okay? Good luck tomorrow. So he could ask you to draw these, okay? Does it have to look exactly like this? No. You could draw it a couple different ways. As long as you have clearly separated hydrogens and hydrogens really close together, he'll give you points. The other thing to know is which requires, or which is most stable, okay? So these hydrogens are kind of like similar charges, okay? They repel each other. So when they're close together like this, they're not happy. They want to, it takes a lot of energy to hold them there. So staggered is considered most stable, and eclipsed is least stable. So he could have you draw them, he could have you identify the names, so knowing eclipsed and staggered, or he could ask about their relative stability. So kind of 3 different questions, yep.
Isn't eclipsed more, it's higher energy?
Yes,
Less
higher
stable?
energy, yep, higher energy, less stable, exactly. Absolutely.
And are you posting the video?
Yeah, after we get done, I'm going to post it to YouTube. Any other last minute questions?
I'm good.
Okay. Yeah, go ahead and turn this off.